Morning, everybody, and thanks to QCware for organizing this important event. So I've been doing these talks for 5 years, right? And talking about our roadmap and talking about what we plan and talking about our vision. This year is a special year for Equal1 because we move from those plans and roadmaps to actual product. We released our first product in March, and we thought about what could we do to show how this is a major leap forward and a major proof point in our vision, right? So our vision is bringing quantum to today's infrastructure, today's data center infrastructure. So what could we do to show that this was a massive leap forward in that vision? So what we did was, yesterday morning, round about 5 a.m., our team in Delft took our quantum computer, put it in the back of a truck on a battery, and drove it from Delft to Paris and set it up in the exhibition outside. So if any of you haven't seen it, we have what we believe is the first working live quantum computer at a trade show. We've done it before in the US, but in terms of other companies, this is a machine that fits into a rack, has everything self-contained, is 1.6 kilowatts, and is fully operational, and we're now doing quantum teleportation algorithms on our 6-qubit array. So that's our vision. I encourage you to come and see us. I'll talk you through the technology. Although this is it is a technology-focused presentation, we do have all of our senior team here, and if anybody wants to talk about customer use cases and applications, we have our applications team here also. So the company was formed 6 years ago on the basis that if we could integrate quantum onto existing semiconductor fabrication processes, we could take the benefit of all that the semiconductor industry has given us. So that's our thesis. If we can leverage the trillions of dollars that have gone into the semiconductor industry, rather than start again and go through Moore's law again, if we could do that, then we would accelerate quantum. We would have huge cost savings because we would be leveraging the money that's already gone into the semiconductor industry, and we could make these in a form factor that fit into rack-mounted form factor. So I often say to investors, quantum is a little bit today like the religious qubit wars, right? And it's all about which qubit is the best, which qubit is going to scale. And I often say Equal1's religion is integration. We believe the only way to scale to millions of qubits is through integration. Now, just in case any of you maybe, that word might not be familiar to everybody, but when we say integration, what we talk about is what's been done in autonomous driving, what's been done in 5G. The reason these technologies have worked is because of integration, because we've been able to put ultimately billions of transistors. If you look at the latest Blackwell or these AI chips, it's ultimately billions of transistors on the same chip. That has enabled, I would argue, almost all of the huge technological leaps that we've had in the last decades. Robotics, 5G, autonomous radar. And our vision, our view, our thesis is that that has to come to quantum in order to scale. So a little bit about the company. We're headquartered in Ireland. We're about 50 people. We have about $40 million in funding. We have offices on the quantum side in Delft in the Netherlands, which I mentioned the guys drove from yesterday, in Sherbrooke in Canada. We have a team in California and a software team in Romania. So I'll talk you through the technology now, because I do think, when in the general, if you look at obviously, the funding rounds have been done in the last few months, silicon spin isn't there, right? Our modality isn't there. So I do believe there's some education in terms of how we're doing it and where it is. And I do believe, frankly, you're going to hear a lot more about this modality between ourselves and our competitors in the next 12 to 18 months. So there's 3 pillars that we sort of base our thesis on. So the question is, how can we get integration into quantum? How can we integrate classical and quantum on the same chip or in the same package? So there's 3 fundamental technologies. Our qubits are what are called silicon spin qubits. I'll go into a little bit of detail on how we fabricate them, how they're made, and what the current performance is. That, because these are termed hot qubits, they operate at 300 to 700 millikelvin today with a path to getting to 1 Kelvin. We can integrate other electronics. That's the key thing. So we can put ARM cores, we can put neural networks, we can put RF generators, pulse generators on the same chip or in the same package as our qubits, and that enables the vision of putting a quantum computer in a single rack. So this is the machine that we announced earlier this year in March. We were hoping to announce our first order here. We're inches away from it, so look out for the press on our first commercial engagement on this in the coming, hopefully, weeks. But this is a fully self-contained, no external cooling, no dilution cooling, no special vibration. Everything is self-contained. As I mentioned, this went in the back of a truck yesterday and stayed cold all the way. So it has all of the cooling inside. It cools our qubits to 300 millikelvin. It's a 6-qubit array today. We have performance that I'll go through, which is competitive with other modalities. It has all of the electronics externally today, but eventually it will go internally. And basically, this can fit into a data center, plug into a standard rack. It's 1.6 kilowatts. Okay, so maybe taking a step back and going through some of the building blocks that we believe is needed for a scalable quantum computer. So first thing is high-quality qubits and a way to make fast and high-fidelity gates. I'll talk through each of these a little bit as to where we are today and what our roadmap is. Second one is a production-grade fabrication technology. I mean, a lot of companies talk about, frankly, having their own fabs, doing this internally. Our view is we need to work with the TSMCs, the global foundries, the Samsungs of the world to make this in a production grade process that ultimately can make qubits of the quality that we're going to need. We think you need cryo-electronics. So we think that with the bandwidth and latencies that we're going to need when you get to hundreds of thousands and ultimately millions of qubits, there is no way physically to come out of the fridge and go back in and get a loop that is low latency enough to do error correction at the scale that we're talking about to be able to do real-world applications. So we've been working for 6 years, and we're on our 6th generation of cryo-controller chip. We have what we believe is the most advanced cryo-controller chip in the world that will go into the fridge to control the qubits. Talk a little bit about error correction and our view on that. And then, again, if you want to go see the machine, please come see us out on the floor. We've got 9 of us here, and we'd love to talk to you about any aspect of this. So, there's a lot of arguments about scalability and which technologies are going to scale. I guess my perspective is I probably don't need to convince anybody here that if we can get CMOS work or qubits working on CMOS or silicon, then that will scale, right? I think everybody knows now, the whole world knows, given the NVIDIAs and where we are with AI, that silicon scales. I think so. For us, I guess it's not a question of debating or arguing about the path to scalability, because we have a process. It's really about, can we get to the point where we're proving that we can do this actually, that this is possible. And scaling takes care of itself to some extent. And again, we've got work to do. We're certainly not there. There's a lot of engineering challenges ahead of us, but we believe, within 18 months or 24 months, we will have demonstrated something that will show that this is the path to scale quantum. So as I mentioned, we use a very small transistor structure. We'll talk a bit about how that is made, and we use the spin of the electron as our qubit. And I guess people ask, well, why now, right? Why is it that these other companies have spent a lot of money on trying to develop new processes, and when you guys are coming in here and saying, well, you can do this on a silicon process? So I think there's 3 answers to that, and they're here on the right. One is the geometries of the processes weren't available when these companies started their quantum journey. So we're only in the last 5 years getting down to geometries that can actually confine the electron. Second on the bottom is sort of the control electronics. We're entering a new phase. I believe this is going to be a new wave of growth for the semiconductor industry, where we're moving. It really is going to be a paradigm shift, where we're moving from essentially controlling a river of electrons to controlling single particles. And that's going to drive a whole wave of requirements and orders of magnitude improvement in noise and precision and what's needed in the electronics. But then maybe the key unlock is this one in the top right, which is spin qubits have been around for a long time. If you looked at these things, look at publications from 10 years ago, you'll see the performance was sort of in the 10 nanoseconds of coherence time. And so essentially, when people looked at this, they said, okay, we can disregard this because it's not going to get to the requirements we need. It was demonstrated experimentally now, I think 6 years ago, that if you purify a layer of the silicon and you remove a certain isotope of the silicon, you get over 100x or more improvement in the qubit performance. And you start to now get into a range where this looks feasible as a qubit that you can scale. So they're the things that have enabled the approach. So maybe very quickly just to talk about how do we make our qubit, how does this work? So first thing you need to do is you need to confine the electrons in 2 dimensions, and we use a 2-DEG heterostructure to do that. There's 2 ways of doing that. One is with silicon sandwiched between an oxide. The other, and the one that we choose, is silicon that is sandwiched between silicon germanium. And that confines, you have a very narrow heterostructure, that confines your electrons in 2 dimensions. You then use gates essentially to electrostatically form your quantum well and confine your electron in the 3rd dimension. So now you have your electron confined, and we use a small micromagnet to basically change the magnetic field that the electrons are seeing from one well to another, which gives you separation in frequency, which allows you to set up a scheme where you can control the electrons. And then essentially to make qubits, you put a sequence of pulses and RF signals on the gates to manipulate the qubit. And I guess if you look at what we need to do in terms of these control lines, and this is not dissimilar from what others need to do, you've got things like pulse resolutions in the 2 to 5 nanoseconds. You've got pretty tough specs on DACs and amplitude control. Again, you're controlling single electrons here. These are very small voltages. You need RF generation. And I suppose our view is again that trying to orchestrate this and control it and keep it synchronized with massive machines outside of the fridge is just going to break down, and you need to have this integrated. So our current results, the paper was published in December. It's got a little bit of an update on the fidelity metrics. We've improved them since. We're at 99.4% 2-qubit gate fidelity, 99.9 almost single gate fidelity, and 70 to 80 nanosecond gate speed. So these are, competitive with the other modalities and where they're at, and coherence time in the 13 microseconds today. In terms of where we want to go, this is sort of the roadmap. We're looking at getting to 3 nines of 2-qubit gate fidelity, 4 nines single gate, 100 microseconds in terms of coherence times, and that really is a platform that you can start to scale. So if we can maintain those as we scale, I think we have a scalable platform. So the next question is, I suppose, well, how do you intend to scale and maintain those numbers? And here, this is an approach that has been shown by the previous speaker, Yuval, and actually this is from the QERA paper here up at the top right, where they're using shuttling essentially to move the qubits to the right place in a grid. And it turns out you can actually do that with silicon spin qubits also. So you can imagine an analogy where you have electrons essentially moving around this grid, which allows you to separate out the gates. So one of the big problems that superconducting and if you do a dense array in silicon you have is, when you pack these things really close, you don't have the connectivity, number one, and you have a lot of challenges in terms of interactions between the qubits. This is a semi-sparse array, so we move our qubits to the area of the grid where you need to do your 2-qubit gates, and you can imagine scaling this out. So, we think once we move to 17 and then 49 qubits in the next 18 months, this will be a big proof point of the scalability of the approach. To switch a little bit then to the controller side, this is the current controller chip that we have. It's operating at down to 300 millikelvin. It's got ARM cores, it's got pattern generators, it's got neural networks that we aim to use for our error correction. It's got all of the pulse generation and detection that you need for the qubits. And our plan in the short to medium term is that the qubit array will be a separate chip up until probably 2-3 years out. So we will be using some of the most advanced packaging techniques to package the two chips. But eventually we see a time where ultimately these things come together on a single chip. But our view is that's a number of years away. Okay, so we have the qubits, we have the architecture that we believe can scale it up. If you then look at our plans for processor architecture, so we plan on making what we call quantum tiles. So the array that you saw is put into a tile with all of the electronics that are needed to make logical qubits. So we have all of the error correction electronics in the tile. We haven't yet put that, demonstrated that together, but we've done all of the building blocks that we need in terms of that electronics. And then we array those tiles across full reticle to make our chip. So, our vision, I suppose, in 10, 15 years is that people, Global Foundries or Samsung will have a quantum PDK that people can take and essentially make a transistor. And our vision here is a fabless, we want this to proceed, and we think this needs to essentially come as the semiconductor industry has come out, where you have a lot of partners around providing IP blocks, whether it be memory, whether it be microprocessor cores. And so that's our vision. We think there's a very nice period between now and then where if we get ahead and we can demonstrate this, that we can become the leader in that. But ultimately, we see this to be democratized in foundries today. so just on the right here in terms of the benefits, it's natively quantum classical, so you can do very fast loops inside of the chip, either for your algorithm or for your error correction. We think it can do real-time error correction, where essentially to the end user, you're doing the error correction under the hood. It's very adaptable. So you can actually adapt it to different error correction schemes, and you can also adapt it to potentially yield issues for the qubits. So let's say we have a yield where 10% or even 15% of the qubits are not reaching the threshold we need. We can essentially train them out or learn them out of the network. So a lot of adaptability, a lot of scalability in the architecture. So then this is, as I mentioned, our first proof point of that. So this is taking the chip that I showed before, which is a 6-qubit device, and putting it in a form factor that is plug and play. So you can put it in the back of a truck, you can put it into your data center. We can have it here on the floor of a show, actually running quantum experiments as what we believe is a major first proof point. Now again, 6 qubits is behind a lot of the others. We plan very quickly here, and hopefully we'll be here next year talking about our next generation chip and increasing the qubit count to becoming competitive with all of the other technologies. And so, coming to the end, I suppose, the vision is this, which is that you don't need to build new infrastructure. You don't need massive. I mean, you look at some of the visions of some of the companies that are talking about what their roadmap is, and these things are massive installations. And a lot of us talk about quantum being able to solve the energy problem of data centers, and there is no way that they're going to solve the energy problem. In fact, they're going to make it more of an issue, right? I think again, our vision is that integration can bring a form factor and can actually bring energy savings as we roll out quantum and for real use cases. So in summary, I suppose, we wanted to do a few things here in Q2B 2025. One was bring a machine, drive it to the show, set it up within the day, and show that this is possible. We have 9 of our team here. So if you want to talk anything from qubits to algorithms to your applications, we have people here that can do that. So please come and engage with the team. And we wanted to give you a sense of, okay, you guys have delivered this and brought this here, but where does this go? And so we've tried to show a plan and an architecture that we think leverages a proven way to get innovative chip products to market. And we've all been involved in many of these products that will scale to millions of qubits, that uses integration to leverage the silicon industry, that can enable real-time error correction, and ultimately can produce these quantum computers in racks, just like GPU, CPU. Thank you very much.
Okay, so we have a few questions from the audience. But actually, before we get to the questions, I need to make one quick announcement, which is that, unfortunately, lunch will be slightly delayed due to a small issue with our catering truck. But they are on their way now, and we estimate we'll serve lunch around 12:30. But in the meantime, we will have, right after the questions for Jason, we'll have a bonus presentation, so don't go away. Okay, so let's get to the questions. Okay, first, what are the main barriers that Equal1 needs to overcome in order to scale from 6 qubits to coherently controlling hundreds or thousands of individual qubits on one chip?
I think, look, the main challenge with spin qubits is controlling them as we scale. And so, all of those signals that I showed, we need to be able to put those on the qubit. You've got, crosstalk issues and others. But I suppose the nice thing, I think, is that there are many of the issues that others have faced to get to where they are today. And there is now companies in the ecosystem who have, done that, and we're partnering with them, where you're using techniques to, like pulse shaping and all of this other thing. So I think it's not going to take us as long as others, because we have the benefit of the learning that, in the last decade, to go from single-digit qubits up to hundreds. And so that's probably the main challenge.
Okay. And before error-corrected universal operations, what application areas do you think that Equal1's quantum computer will be useful for?
Well, I suppose that's the debate of, the reason we're releasing this, and actually, we get this a lot, is what good or what use can a 6-qubit machine do? And I suppose there's two things, really. One is, getting into understanding quantum, and so if you wait, and I think everybody here in the audience would agree, if you wait until quantum is here, it's going to be too late. So I think there's a lot of appetite to start to dip your toe in and start to do building blocks of what will be these quantum algorithms, because this is a very different paradigm to classical computing. I guess that's a general industry answer. The specific Equal1 answer is, if you look at this machine, we can upgrade a customer by changing out a PCB from generation to generation. So if you think about the ROI that we can offer, it's a much different proposition to others, where every generation you're potentially spending, tens of millions. We can actually offer a really cost-effective solution where you can, keep the cryogenics potentially and upgrade with a PCB. So that's a very different paradigm than what others can offer.
I see. Okay, next question. How many qubits do you estimate you'll need in each quantum tile to make at least one logical qubit per tile?
Okay, so these are good questions. So I guess the first thing is, I don't think there's a universal definition of what a logical qubit is. I think if you look around, people use their own definition, right? So I'll answer that, I guess, in two ways. You could define a logical qubit as getting over the error threshold. So you're going from error correction hurting the system to, barely over the error correction, but you're only getting, a small uplift. And there, we think we have a shot. It's not, it's not certain, but we think we have a shot at with our 49 qubit chip, which we'll have again in sort of 18 months, to do that demonstration. So that's just about getting over the threshold. But in reality, that's not, I think, what people mean by logical qubit. If you're looking for, 6 nines or something like that, that's sort of going from 99.9 to maybe 99.95. Or so I guess it comes down to the error correction scheme. And if you look at surface codes, again, we think once we get into the hundreds, we can start to get into the numbers that start to increase the orders of magnitude for error correction. But happy to talk more at the booth if people want to discuss that.
All right. Thank you very much for those answers, Jason. And let's thank Jason again.
Thank you.